All right, what happens if you have multiple groups on your ring? What happens if you have two or more groups? Well, it's an additive effect. You have an additive effect. But you also have to look to see which one is more activating and which one's more deactivating. Your more activating group trumps your more deactivating group. Okay? Now, in this case, you have an additive effect. Okay? Your methyl group is an orthopara group. So that means here's the ortho spots, and then here's the para spot. Now the para spot already has a group, so I can't put another group there. So this carbon is off limits, so that doesn't really matter. Now my nitro group is a meta director, so meta to this nitro group would be this position again. So you have this additive effect. So the question is, when you nitrate this, is the nitro going to go on these carbons, on carbons 1, or on carbons 2? Well, I think we've realized they're going on carbons 1. So I'm going to get 0 product of a nitro group there. And that's exactly what we see. 99%, I mean that's huge, of the nitro group ortho to the methyl, meta to the nitro. Okay? So we'll see other examples of how the more activating group trumps it. But for right now, the directing effect of the two groups may reinforce each other. So it's reinforcing. It's an additive effect. Okay? What happens if you have two of the same groups? Okay? So first look at this methyl. This methyl's here. Orthopara of this methyl. Here's ortho, here's para. Okay? What about this carbon? This carbon, this is ortho, and this is para. Notice again, we have an additive effect. Nothing is going here. Notice that. Nothing's going there. Okay, now, putting a group here, or putting a group here, gives me the same compound, gives me the same compound. Okay, group here is the same as a group here. But what about this position? Okay, that can give me another compound. Well, notice, remember we talked about hindrance? Well, this position, all right, is hindered by two different groups. So you're really not going to get a lot of product there. Most of it is going at that carbon right there. And you see about 65% of it does go at that spot. Okay? So the position in between two groups in the positions 1 and 3 is hindered for substitution, and it is less reactive. Okay, so what happens in this case? This is an orthopara, so at the blue spots. This is a meta director, so that one, and then obviously this spot, but that spot's taken. So I can go pretty much anywhere, right? Well, no. In this case, I don't have an additive effect. So what happens if you do not have effect? So no additive effect. So what happens? The more activating group trumps the deactivating group. So this is as if I don't even have this group on here. Basically, this guy's in charge. This guy tells where the group goes. Now, this position is too hindered. All right, too much stuff is around here. So I'm going to get there, and I'm going to get there. Now, these groups are very similar in size. How do you know that? Just look at about the number of atoms you have. You have about 3, 4, 5 atoms here and about 3 atoms here. Maybe that's a little bit bigger, so you might get more of it at this spot right here. But pretty much, these are the two spots that you're going to get compounds. And you can see it's one right there and one right there. But I'm not going to get any here because that's meta to this, which that's not a meta director, but this is a deactivating group. And that's a little bit too hindered. Okay, so if directing effects oppose each other, the more powerful activating group has the dominant influence. So here's a solved problem. Predict the major product of bromination of parachloroacetanilide. Okay, see, even I have trouble saying these things. Acetanilide. All right, so we are brominating this compound. So Br2 with FeBr3. Okay. What type of directing group is this? Okay, this is an orthopara. Remember, there are lone pairs on this halogen. What type of directing group is this? This is also orthopara. So the chlorine is going to direct here, and obviously in the para spot. but I have something. Oh, I don't know why it's doing that. Sorry about that. Okay, so here and here, and then this nitrogen is also an Orthopara director, so it's going to go here or here. So technically I can get it anywhere on the ring, but which one is the more activating, the nitrogen or the halogen? All right, the answer is the nitrogen. We've learned the nitrogen's more. The chlorine is Orthopara, but it's deactivating. The nitrogen is more activating. So you're probably going to get the bromine at that position right there. So your product bromine would be that compound. Okay, so there you go. The amide group is a strong activating and directing group because the nitrogen atom with its non-bonding pair of electrons is bonded to the aromatic ring. I don't have to read this, you guys can read it on your own, but the amide is more strongly activating than the chlorine. All right, the next reaction, 17.10, Friedel-Crafts alkylation. This is just another reaction. Friedel-Crafts are two scientists. They won the Nobel Prize for this reaction. You're making a carbon-carbon bond. I think I've told you carbon-carbon bond formations win Nobel Prizes. They're that big. So basically, this reaction is this R group has to be a carbon that's sp3 hybridized. So it's got to be a carbon with an X on it. You got to add some sort of Lewis acid. We're going to talk about different Lewis acids, either aluminum or the iron, and you can put a carbon group on your aromatic ring. So you're making a carbon-carbon bond. Here's a carbon and whatever carbon you have on your R group. So you can make toluene, you can make ethylbenzene, isopropylbenzene, terbutylbenzene, whatever you want. Okay, so it's a synthesis of alkyl benzenes using Lewis acid. The reaction. Okay, now here's the important thing. The alkyl halide reacts with the Lewis acid. This becomes a carbocation. Now, what have we said about carbocations? What badness can happen with carbocations? It's the R word, rearrangements. Okay, so this is a limitation to Friedel-Crafts alkylation. However, they came up with a really cool way to fix it, which we'll talk about. Let's first talk about the mechanism. Chlorine attacks your Lewis acid, we've seen this before, to form your carbocation. Now in this case we're using tertiary, so there is no rearrangement on this one. Okay, you form your sigma complex, this plucks off your hydrogen, forms HCl in your catalyst, and you put your group on your aromatic ring. Okay, you can do the same reaction with a double bond. It doesn't have to be an alkyl halide. Double bond plus HF makes a carbocation. Right? All you need is a carbocation. It doesn't matter how you get to here. There's several ways of how to get to a carbocation. One way is with the alkyl halide. Another way is with HF. Okay. Another way is with an alcohol. Take an alcohol plus a BF3. Boron's a pretty good Lewis acid. Plucks it off, making a carbocation. All right. Now here are the limitations. Okay, reaction fails if benzene has a substituent that is more deactivating than halogens. So if you have a deactivating group on your aromatic ring, you're really not going to do a Friedel-Crafts. It's going to be hard to do. But the main one is rearrangements. That's the one that I kind of want to emphasize the most, are the rearrangements. Okay. The other thing is that the compound is more reactive than the original compound. I'm not going to stress too much on those. It's really the rearrangements. Here's an example. Okay, 1-chloropropane. What happens? You form this complex. Okay, the chlorine starts adding to the aluminum. So that starts forming a primary carbocation. How happy is a primary carbocation? Not very happy. This is a sad, sad carbocation. However, a secondary is much better. So you have a hydride shift. You immediately have a hydride shift to form this carbocation, a secondary carbocation. Well, obviously, if I wanted this compound, I would have started with the chlorine there. I obviously want the propyl, but that's not what happens. You get a rearrangement and you form isopropyl. Okay, so this is the compound that obviously this person wanted. Let me show you. But that's not what they got. They got the isopropyl because of the rearrangement. So that's one of the limitations to Friedel-Crafts. Okay, so devise a synthesis for para-nitro-tert-butyl-benzene from benzene. Okay, so this kind of summarizes a lot of it. I have a benzene ring, okay, and I want to synthesize tert-butyl-para-nitro. Okay, well, this is a meta-director, and this is an Orthopara director. And these are para to each other. So if I were to put the nitro on first, let's say I were to synthesize the nitro first, and then I went ahead and did my Friedel-Crafts, where would the tert-butyl go? Well, this is a meta-director. My tert-butyl would go right there. I would form meta-nitro-tert-butyl-benzene. Okay? So obviously I have to put on the tert-butyl group on first. That's an sp3 carbon. So that tells my nitro group, remember to make the put on the nitro. So you have to put your tert-butyl on first. So in this chapter you have to kind of plan out your synthesis. All right, and to make this, your tert-butyl, that's the Friedel-Crafts. Tert-butyl chloride plus aluminum trichloride. So you got to first do this, then you do this. It's got to be in this exact order. If you reverse it, then you're going to get the meta compound. Okay, so apparently, let me erase all this so that you can see it in action. It might be a little bit neater too, but I want you to realize that that's the types of synthesis problems that we do in this chapter. Is you have to plan it out accordingly. So the good way. First, you're putting on your Orthopara group. This is Orthopara. So it tells, plus you have a tert-butyl group. This thing is going para. It says plus oro, but I would say that that is less than 1% ortho. If you put the nitro on first, nitro is deactivating, plus it's a meta-director. So it's going to direct it at this position right here. Okay, so there you go. The next reaction is the Friedel-Crafts acylation. This case, same type of reaction, but in this case you have an acid chloride, and you're putting on an acyl group. Acyl implies a C double bond O. So rather than just having an sp3 carbon, you have actually an acid chloride. And whatever carbon has a chlorine on it, which is the one with the carbonyl, that's what gets attached. There are no rearrangements in this case. Okay, whatever carbon this is, that's what gets attached on your ring. Okay, so these acyl groups are very good reactions. They are used in place of alkyl chlorides. The alkyl chlorides have, like we said, have a lot of limitations. It works well in some cases, but not in all cases. But this route really works well, and this was kind of their fix. Okay, your product is a ketone. It's a phenyl ketone. Phenyl meaning aromatic ring, and you have a ketone. Okay. The mechanism, just like all the other mechanisms, the chlorine attacks to Lewis acid. You form this acylium ion. They've actually proven that this thing exists. It's a very highly activated carbonyl. So your pi bond attacks it. You then have your base come over. Whatever your base is, it's your aluminum, will come over and pluck off that hydrogen and reform your aromatic compound. Okay, there you go. I wrote it on the last page, but it's right there. Okay, so here's a hint. Friedel-Crafts acylations are generally free from rearrangements and multiple substitutions. They do not go on strongly deactivating rings, however. Okay, now here's the thing. I have a carbonyl now on my compound. Let's say I don't want the carbonyl. You remember last page I wanted to make this propyl, but it kept doing a rearrangement. Well, Clemmensen came along and said, well, I'm going to create a reaction that's going to completely get rid of this carbonyl group. And here it is. It's a zinc mercury amalgam with hydrochloric acid. So you can do whatever group you want. You can attach whatever group you want here doing the Friedel-Crafts acylation. And then you can get rid of the carbonyl with the Clemmensen reduction with the zinc mercury amalgam and hydrochloric acid. It's a very useful reaction where now you can start making whatever compounds you want. So the Clemmensen reduction is a way to convert acyl benzenes to alkyl benzenes by treatment of aqueous HCl and amalgamated zinc.